and welcome to the second video of the FP3 chapter Differentiation. On the screen, to review our previous 3 results, if you've got time, pause the video and write these down. For sinh, we showed in the previous video that you get cosh, and if you differentiate cosh, you get back to sinh, and if you differentiate tan, you get sech squared x. And these 3 are given to you on the formula sheet, but you may be asked to prove them. In this video, we're going to do something very similar, but we're going to do it with the inverse hyperbolic functions. So again, you've got these in the formula booklet, and possibly you've seen them and you know what they are, but you might be asked to prove them. So I'm going to do the same as I did in the last video. I'm going to go through one for r sinh, and I'll leave you to go through the other 2 because it's a very similar process. This is a little more involved, however. So the trick to this, the trick to all 3, is your starting point. Don't try and differentiate r sinh x directly because we don't have any information on how to do that. But what we can do is make this equal to y, and then remembering that r sinh is the inverse, we can take that on the other side, it becomes sinh, and we've just gone through how to differentiate sinh. So we can differentiate this either by doing dx by dy and then flipping it, or by doing implicit differentiation, which is the one I'm going to choose. So if we differentiate x, we get 1, differentiate sinh y, we get cosh y, and because that's a y, not an x, we need to apply the chain rule and multiply by dy by dx. Then I can rearrange this. I like my dy by dx on the left. So on the right we would have 1 divided by cosh y. And this is the same starting point for all 3. Take the thing you're trying to differentiate and bring it onto the other side with a y so that it's back to sinh, cosh or tan. Then apply differentiation either implicitly or with differentiating with respect to y, and get the result that you get. Now from here, we don't want y to stay here, obviously. We want it in terms of x. So from here we need to relate this result back to what we had equal to x. So I need to get cosh y in terms of sinh y. And that's true for the 3. You'll have to get whatever you find the result is and relate it back to what x equals. It's a little bit different with the tan, but the sinh and the cosh will both use this same identity I'm going to use, which is that cosh squared y minus sinh squared y is equal to 1. With the tan, you'll need to use a different identity, but it is still an identity. You're trying to relate the thing that you're getting with something that can be turned back into x. In this case, if I rearrange, I get cosh y is equal to a 1 plus sinh squared y, and then a square root. And I'm not going to put a plus minus on that for reasons I'll talk about in a few minutes. So cosh y, I can replace that with 1 plus sinh squared y and the square root. And then I know that sinh y is equal to x as part of my working out at the top. So now this is 1 divided by the square root of 1 plus x squared. And this is the derivative of r sinh x. So I'll go through quickly one more time. It's the same with cosh and tan. Take this out, make it equal to y, bring this on the other side, differentiate the function using what we did in the previous video, and then relate your result, whatever that is, back to the thing that is equal to x using an identity. Cosh and sine will use this identity, you'll have to look for a different identity. Once you've got it back in terms of that, replace it with x, and then that is your result. And the three results that you should get are this one that we've just done. I'll talk about the plus negative at this point. I'll do this one by one. So the reason I haven't put a plus negative on that square root is because of what it actually means. I'm going to do this in terms of the graph. If you put this on a graph, what you get is something that kind of looks like this, and this is our sin x. And very simply, I'm going to justify this by just saying there is no negative gradient on this graph. Although mathematically, when you do a square root, often you should have plus negative options. Here, when you consider what it means, the gradient of this function, there is no negative. So I don't need it. And if I were to put it in, it wouldn't be true. Okay. The second result, if you were to do this with r cosh, you should find this, a very similar result. But it's limited to x is greater than 1. On the surface, you might say, oh, that is so that this square root is not negative, and if x is less than 1, then you will have that problem. We don't want complex numbers or anything like that. But it doesn't explain why it's not the magnitude, because if I put x is equal to 2 or minus 2, mathematically they would both work. But minus 2 is not okay. And again, I'm going to use the graph to explain this. Because if you remember, we had, let's go all the way back to cosh. Cosh was this thing. And there was also a bit on here, but you've got to be careful. You cannot do the inverse of a function unless it is 1 to 1. So I put this in dash because we're going to ignore this in order to make it 1 to 1. So we can have the r cosh, which I'll put in green here. That is r cosh x, where we have limited it. X is greater than 1. So it's coming from the fact that there is no graph less than 1. Even though if you went less than minus 1, mathematically this would still be okay. It just isn't there on the graph. And you can see also in this section on the green here that this is a positive gradient. So again, there's no negative over here. But you might come across a question that's a little bit sneaky. Because if I put in yellow this side here, instead of taking the blue branch, instead of taking the positive branch for the 1 to 1 function that we inverted, there was no strict reason why I ignored this and took this. I could ignore this one and I could take this branch, and that would give me a 1 to 1 function that I would also probably call cosh x. And if I inverted that, oh, I'm running out of colours, red. If I inverted the yellow one, r cosh would then be this. And x would still have to be greater than 1. But you can see here in red, the gradient would always be negative and it would never be positive. In which case, my gradient would have to have a minus sign in front. But you won't see plus minus, you won't see this in the definition because you can't have both of these at the same time. Because in order to have r cosh, the cosh that you're inverting needs to be 1 to 1. You can only choose this branch or this branch. You can't have both on the inverted cosh function. So it's either or. You can't have them both in the definition. Although there may be contexts where both results are valid answers. So just be a little bit careful here. You might occasionally have a plus minus in the context of the question. But as part of the definition, you won't. Okay, that one was the most complicated one. R tanh is this result if you go through the process. And similar to this restriction, this is restricted just because there is no graph outside of that range. R tanh looks something like this. And we're not limiting it like we were with the Koch curve. These are just asymptotes. And there is no graph outside of x is minus 1 and x is 1. So it's part of the domain of the graph. So here are your three results. And over here, a bit of an explanation as to why the plus minus isn't here and why these restrictions are here. And again, these are on your formula sheet, so my graph is in the way. These are on the formula sheet down here. Okay, a couple of examples. The first one is quite quick, because if the question doesn't ask you to prove it, you don't need to go through all of that proof. You can just use the result on the formula sheet, and the result is this, the one that I'm going to use here. So differentiating this, use the product rule, I differentiate x, I get 1, I leave this alone, and then leave this alone and differentiate r cosh, I get the result in white. And then I should just tidy that up. And there is my result. I guess if I was really formal, I should put x greater than 1 there. But you would not normally lose a mark in an exam for that. Okay, a second example. Given that y is equal to this thing squared, prove that this is true. Okay, here I'm going to apply the chain rule. So the derivative of this is equal to the power on the bracket comes down, 2 times the bracket, times the derivative inside the bracket, which if I look on my formula sheet, well, it's the same one. I have 1 divided by the square root of x squared minus 1. Now be careful with your notation. Of course, this thing here is not the second derivative, but is the first derivative squared. So I take this and I square it. Maybe I should just tidy that up first. That's 2r cosh x over the square root of x squared minus 1. So the derivative squared is 4 r cosh x squared divided by the square root. Squared just gives me this thing inside the square root, and I'm almost there. I want the x squared minus 1 on the other side multiplied by the derivative squared, and I can see r cosh x squared is the definition of y. I'll do it in 2 steps, just so the examiner can smile and feel like I know exactly what I'm doing. And there we go. We have proved the result, and the final step was exactly how they wrote it. So that should be enough for you to do questions from exercise 3b if you have the textbook, and maybe I will see you in the third and final video for this chapter.